unless I'm mistaken.
All right, we are going up. Hello, Internet. We will be getting started in about 10 minutes.
Yeah, so streaming should literally show up on my screen, right?
If you're on the correct link, it should.
I'm on the YouTube DVAA site.
Yeah.
September, there you go. There you go. It's blurry.
That's the camera. Yeah, the camera has a very short focal depth, so it's in focus if you're right near it.
So I have another camera which we got, which I have to.
Yeah,
set
we
up
should
the
use that.
next one.
This is the finest $18 Amazon
No.
camera.
We own $170 camera.
USB.
It's USB.
All right, then we'll use that.
Yeah. By the way, I moved my hand and it was like a minute.
Sometimes it's slow.
Crazy,
Yeah,
crazy.
it should be 25 to 30 seconds.
No, I know. Because you don't do that priority thing.
Yeah, we can't do that here. All right, and we should switch over to the shared screen. Yeah, so this goes the opposite way that you think it does. So the next slide is the down. The previous one is the up.
See, this is what you get when you
Finest
truck
Amazon.
with people who
engineering.
use, Microsoft, get these weird. Okay. All right. Well, I've got a green one for backup in case.
Wow. I am seeing your presentation and so life is good.
Very good.
Well. Yeah. Right. Exciting day. I think I should. Oh, we're.
All right, we got quite a few people watching. We'll be getting started in just a couple minutes.
Exactly. I have a goal. Actually, probably what I should do is look to see how many of us there are.
Oh, it got quiet. We still got 1 minute. Yeah, that clock is about 6 minutes slow or 5 minutes slow.
So what time is it really?
7:29.
In either case, we're in control of our own destiny. We can do whatever we like.
But time is relative, isn't it? Yeah. We could tow in a black hole and then we
Yeah.
could be here as long as we want.
None of my relatives are good at keeping up with time.
Yeah,
Am I expecting questions in the middle or?
whichever you prefer.
Feel free to question the audience too.
All right. Should we get started? All right, I want to welcome you all. This is kind of a new thing for us. This is going to be a joint meeting of the Southeast Pennsylvania section of the AAPT and the Delaware Valley Amateur Astronomers. So I think maybe we'll start off with a little friendly competition. Who's here for the DVAA? Who's here for the AAPT? I think DVAA wins by a little bit. Okay. I lose the bet. All right. So my name is Jeremy Carlo. I'm the president of SEPS, and I'm also the programs chair of the DVAA. So I'm, I guess, a double agent. So that's why I'm up here. All right, let me share my screen here. There we go. All right, so I'll start by explaining a little bit about both of our organizations. Let me activate this here. So the AAPT SEPS is the Southeast Pennsylvania section of the American Association of Physics Teachers. So the AAPT, the American Association of Physics Teachers, is a national organization covering the entire United States. And SEPS is the regional section, which roughly covers the 5-county region around Philadelphia. We also have some membership from South Jersey, from Delaware, even a few from Maryland and other parts of Pennsylvania. So a little bit about both of these. The National AAPT is a professional membership association of scientists dedicated to enhancing the understanding and appreciation of physics through teaching. I just lifted that from the website, but it kind of gives you the idea of what it is. So it's a nationwide professional society. It includes physics educators at mostly the college level, but also some high school teachers. And they host two very large annual meetings called the winter meeting and the summer meeting in various places throughout the country. They actually have a nice rotation going back and forth between East and West. Usually the winter meetings are down south, so the weather's a little bit nicer. They do a number of other things, including workshops for physics teaching, workshops for physics teachers and faculty members, a number of DE&I, that's diversity, equity, and inclusion initiatives, a lot of job postings, guidelines for curriculum evaluation, recommendations regarding programs, a number of different topical working groups, as well as funding opportunities. SEPS and the AAPT sections in general exist to provide a local connection to the national organization. And the way I think of it is that we have kind of a lower barrier to entry. Our annual dues are cheap, they're $10, right? That's a bargain anywhere. And in fact, the first year we pay for them. So it's a lot easier to get into. And we also have two annual conferences. Well, one sort of big conference, which is what we're doing now, and then a smaller thing that we call demo day, kind of people just show up and you put your name on the board and you get up and spend 10 minutes talking about what you're working on. So it's really a great thing. And it's right in the Philadelphia area. So you don't have to book hotel rooms or fly or get into fist fights with flight attendants or anything like that. It's right there. That's why I say it provides a lower barrier to entry. It's a lot easier to get involved. I think we've got about a 50-50 mix of high school and college folks, which is kind of nice because the two groups really don't talk to each other very much, right? I've been on the college side for a long time and people on the high school side. There's really not much mixing. So that's one of the things that we do very well. So in addition to that, we have some periodic workshops and we have a nice email forum, which is actually new. You can post job postings and discussion of various ideas. So the current officers, I'm the president. Our vice president is Paula Miller at Abraham Lincoln High School. Our secretary is Ryan Batke, who's at UPenn. Our treasurer is Mark Barron at Sun Valley High School. Our section rep is Amber Stuver, also from Villanova. Our past president, who actually kept us kind of alive through COVID, was Laura Williams. She's at Bodine High School. And our webmaster is Mark Scafonis. And we do have a new website. So that was an issue for a while, but we do have a new website, which is now working. So the meeting, the bulk of the AAPT meeting will actually be tomorrow at Villanova University. We'll have a number of different talks. We'll have Barry Thierman, who I think is very well known to everyone in SEPS. He'll be telling us about his 41 years experience in teaching and what he's learned from all of that. In the afternoon, or rather later in the morning, we'll have Nicole Castilleja Bentley, and she'll be telling us about some opportunities for faculty to actually get paid to do research at national labs. And then in the afternoon, we'll have contributed talks, demos, and also a workshop led by Barry. So that's tomorrow's events, which will take place at Villanova. So I think with that, I will turn the floor over to Jan, who will tell us about the Delaware Valley Amateur Astronomers.
Hello, everyone. It's great to see all of you here. And I want to thank, my name is Janet Rush. I'm the Vice President of DVAA. I'm standing in for our President, Harold Goldner, who is not here tonight. I want to thank Jeremy for this idea to have this joint meeting because it's a very logical connection. I think we cover the same, sort of the same geographic area. And in fact, some of our physics teachers probably, especially at the high school level, probably run astronomy clubs, and we like to make those connections locally. So I think this is a great idea. And thank you for all for being here. DVAA is a nonprofit volunteer-run organization of amateur astronomers based in the Philadelphia area. So we cover all kinds of different kinds of people, accountants, clerks, lawyers, we're a mix. We just share the passion for astronomy, and we're all amateurs. So that's the basis of our organization. The mission, as per our bylaws, are to aid and encourage amateur astronomers in observation and scientific research projects, to encourage cooperation and the exchange of ideas among amateur astronomers, and to interest and educate the general public in the science of astronomy. Oops, wrong way. Sorry about that. So we have a number of public outreach activities. We have monthly star parties, which take place at Valley Forge National Historical Park. These are open to the public, and we'd be happy to have any of you visit us there and for you to tell your students about this, because it is a great opportunity locally. We have monthly astronomy related presentations. That's where you are here tonight. Again, these meetings are open to the public. And we have star parties and solar observing that we do with community organizations, with educational organizations, with schools, libraries, and scouting groups. A lot of different groups will call us and say, we want to have a star party at our institution. Can you send someone over with a telescope and to help us run it? And we love to do that. We also do educational presentations to community groups, libraries, scouting groups, etc. So that's pretty much a sum of our outreach. Now, if you'd like to get involved in some of the stuff that's coming up this month, our next star party at Valley Forge, this will be the last one of the year, is November 12th at 5 p.m. We'll have a monthly meeting presentation just like this one next month, and that's on November 11th. And the topic of that is exoplanet science from the TESS mission. And we have a community star party at Armand Trout Preserve in Bluebell on October 18th. Details on any of these are at our website, and that's www.dva.org. So I encourage you to check it out. And if you'd like to be on our mailing list, there's a place to click, and that'll get you on the mailing list for our monthly newsletter, so you can find out what we're doing all through the year. Now, what happens inside the membership, in addition to our public events? We have a lot of occasions where we just do casual, collegial, dark sky observing. So we'll meet up together, bring our telescopes, and have a good time observing and learn from each other. We also have telescope and observing how-to clinics, and we're having one of those tomorrow, where we'll invite members to bring their telescopes. We get a lot of interest from newer members, and then the people that are more expert with telescopes will come by. Hey, are there any physics teachers who have a telescope at their house that they don't know how to use? Good. Okay. We
can help.
If you do, we can help with that, right? We have astrophotography workshops. Very, very popular now is folks getting into astrophotography. And so we have a lot of club members that are not only very passionate about it, but really good at it. Take a look at the photos on the website. You'll see that. And we have telescope rentals. So here's one of our telescopes. We have a number of telescopes, beginner telescopes that we can rent. They rent to members for $10 a month. So it's a bargain. And we have astronomy trips that we run with membership. Now, one thing we especially wanted to mention that could be of great interest is we started a new program last year to give awards to youth for astronomy projects. So basically, these are monetary prizes for elementary, junior high school, and high school applicants. I went the wrong way. Sorry about that. So in order to find more about that, just check out our website. That's www.dva.org. Click on Youth Awards, and you'll find all about how to submit. And please share this with your students. We'd love to have some of your students submit projects to us this year. And the awards, all winners will receive a certificate, a one-year complimentary membership in the DVA, and they'll be invited to present their work, such as a poster at a DVA meeting. And all entrants will receive an honorary mention certificate. So the cash prizes, as you see, are first prize $250 for elementary and junior high school, and then $500 for high school. So of some interest to people, hopefully. And the judging criteria are scientific methodology, hypothesis, all the good stuff you teach your students about every day. And the deadline for submissions is May 1st. So plenty of time still to do it. And there's the address. All this information is on the website under that Youth Awards tab. Okay, now we have a little bit of a business meeting to accomplish here. So I just wanted to invite a couple of our chairs to present their reports. Brian? Wow.
Richard Smith, Kelsey Smith, Kevin Hutt, Fraser Rock, Samuel Trent, Susan Burton, Michael Harris, and Daniel Paul.
Wow. Is anybody here?
Don't think anything like this.
Oh, okay. We'll see some of them tomorrow. They're coming to the clinic. No, they are.
I'm pretty sure Daniel will coming.
Yeah. Okay.
Cool.
Lewis.
Hi, I'm Louis Berman, and I'm here to ask for your money. That's literally why I'm here. But it is where, it turns out that your money does help the club actually do our mission, which is doing meetings like this, outreach, renting equipment, and so forth. We're about to have our annual turnover. It turns out that I am term limited out. Harold Goldner, our president, is term limited out. So we're going to be voting in a new raft of victims, officers in January. And so the club is still very vibrant. If you have dues, we're in the pending. We're going to start sending you reminders to pay dues coming up until the end of this year. And thank you for your support.
Yeah.
Lou isn't here, and
Lou isn't here, no, but Barry is going to give us a report, and maybe you should stand here so the camera can see you. I should have.
the camera actually is not going there.
My toupee on straight?
Uh,
Okay.
Oh, okay.
I can't tell you
Where should I stand?
Right
How about
here.
right here? Okay. I'm the chairman of the Light Pollution Abatement Committee. And that consists of two of us. And on this coming October 22nd on Saturday, we have an exhibit at Temple Ambler campus in their event, which they call the Science of Scary. So I don't know what this consists of, but I'll have a light pollution exhibit there. And it's at Temple Ambler in Bright Hall, 1 p.m. to 4 p.m. So you can come, there's no charge. And I'm thinking of it as a community science fair. So we'll see.
Cool. And on the website.
Okay, I guess, Jeremy, maybe you could introduce our speaker.
All right.
There's 17 people.
All right, this is almost a record speed business meeting that we got through here. Hey, don't worry, the SEPS business meeting will be tomorrow. And actually, our elections are tomorrow, which means I won't be president anymore after that.
Stop
So I've
closing.
got less than 24 hours to go. So take that, Harold. You're still in for another 3 months. All right, so let me switch hats here. Back to my programs chair position. So next month, as Jan mentioned, we'll have Rick Schwarz, who's a DVAA member, and he's going to be talking about his exoplanet research that he's been doing. So actually, an amateur astronomer using his telescope is doing follow-up observations to detect exoplanets. So he's going to tell us about what he's been up to. This month, it gives me great pleasure to introduce my colleague, Dr. Joey Nielsen. He's an assistant professor of physics at Villanova University. He did his PhD at Harvard University. He did postdocs at Boston University and MIT. So some little no-name places no one's ever heard of. So Joey's research involves black holes, neutron stars, accretion disks, and particularly X-ray studies of them. Joey's also involved in the Event Horizon telescope collaboration, which recently imaged the black holes at the center of M87 and the Milky Way galaxy. And for that, he was one of the recipients of the Breakthrough Prize. What year was that?
That would be 2019.
2019. So what have you done lately?
Well, as you said, we've imaged the black hole at the center of the Milky Way.
All right. All right. So with that, I will turn it over to our speaker. First, I just need to bring his
Standing here.
presentation up. Let me do this. Yeah. Sorry, I just have to bring up his presentation here, which is there. Eventually, we'll get a hang of this technology. There we go. And now I got to share the screen over here. All right, you can take it away.
All right, can I
And
take
you're
away
on.
the
You can
laser
take that away too.
All right, thank you very much for the intro. It looks like we're a little bit laggy here with the video. It's great to be back. I was here 3 years ago, and it was just before we had released the initial images from the Event Horizon telescope. So I wasn't actually able to say anything about it for fear of being blacklisted or blackholed maybe. But spaghettified. This is one of our for the worst offenders, right? So it's actually really fun to be back now and to be able to tell you about some of the results that are coming out of the Event Horizon telescope and what they mean and why they're interesting and important and how my research group at Villanova is trying to contribute. So this is one of my favorite images of the Galactic Center. This is a multi-wavelength image that combines X-ray, optical, and infrared. And Sagittarius star, our supermassive black hole, is right in the middle. And the image that the Event Horizon telescope has just put out of Sagittarius star is right here. So I'm gonna eventually get you to the point where we can actually talk about this image and what it means. Okay, so let's see, are we going to advance this way? We are not. Let's see. Oh, I'm probably.
Yeah, we just got to make that the active screen.
All right, now there we go. Okay, let's start with black holes. I like to say, let's imagine that this is the sun, and you can see the radius just at the corners, right? The edges of the center of the sun's here, and the edge is there. What does it take to actually turn the sun into a black hole? Well, you have to shrink it down and down and down and crush it into a smaller and smaller and smaller space. And if you crush it to a region this big, it's still 2,000 times too big to be a black hole. So the just to have a sense of what that means, you have to crush the sun into an object that's has a radius of 3 kilometers in order to turn it into a black hole. So, so we can think of what is a black hole. Well, a black hole is an object whose gravity curves space-time to the point of creating what we call an event horizon. The event horizon is the point of no return. It's the surface that once you go through it, or a region that once you go through it, you can't come back. So it's another way to think about a black hole is that it's a region of space that you can't get out of. Actually, kind of, from that perspective, it doesn't matter what's inside it. Once you go in it, you can't come back out. So, so that's one way, a couple ways to sort of think about a black hole. Geometrically, what is it? Well, we have this imaginary surface, this boundary called the event horizon. And again, that's not a physical surface; it's an imaginary surface. But nothing comes out of that once it goes in. And the way that we think of all of the mass, if you imagine a star, that sun that collapses and becomes a black hole, well, once you crush stuff that much, once you compress it that much under the force of gravity, we don't know of any other force in the universe that can stop that collapse. So what that means then is that there's nothing to resist gravity at that point. All of the matter that made up that star should be compressed all the way to a point at the center. And we call that point a singularity. It's a point of infinite density. We don't actually describe this point with the math of general relativity. This is truly that's where the hole in space is. This is a tear in the fabric of space. So we kind of look at everything around it and say, okay, we're not going to think too much about that particular point. So so this is the basic anatomy of a black hole. There's obviously a lot more complicated mathematics that I'm not really going to get into today, but that's the basics of how a black hole works. So so I said when I introduced you to the idea of a black hole, I said a black hole is a thing that curves space. So I want to talk a little bit about what does it mean to curve space, and to talk about what does curved space mean. It's helpful to start with what's flat space. And flat space is space where the Pythagorean theorem works, where you can measure, you can figure out the distance between point A and point B by taking a little distance in Y and a little distance in X. And the square of the hypotenuse is the square of the sum of the squares of the sides of the triangle. That's flat space. And it's actually not very complicated to see why that wouldn't work if space was curved. Well, think about a point, near the North Pole and somewhere else on the surface of the Earth. The distance that you have to travel to get from here down to here, well, that's very obviously not the square of these two distances, the sum of the squares of those two distances. It's longer. So, so a simple way that you can think about curved space is spaces where the distance between 2 points is different than what you would get if you just use the Pythagorean theorem. And by the way, feel free to interrupt me if you have questions as we go along. Okay, so that's a simple sort of a two-dimensional example. The Earth you may surprise to know, is three-dimensional, but in relativity, we actually think about 4 dimensions. So we live in 4-dimensional space-time. And so if we're going to measure the distances between points, we need to include time as well as distances in space. And so this, just to show you a simple example, is how we would measure the distance between 2 points in space-time. And there's one funny thing that I want to point out just as a sort of a curiosity, which is that you include distances in time as well as distances in X, Y, and Z, all of your 3 spatial dimensions. We have a minus sign in there. So that means that in relativity, distances between points can be 0 or they can be negative, which leads to some very interesting results and some results that are a little bit counterintuitive. But all of the really interesting math of relativity, the time dilation, and the Einstein's fun thought experiments that you might hear about when you hear about special relativity, for example, really come down to the fact that there's a minus sign in the way that we measure distances. So things get wild there. And I'm not going to go into that too much, but it's worth knowing that a lot of that is just because of this one little minus sign. Okay, so why does this matter? Why does this idea of curvature matter? Well, if you think about traveling from one point to another, going from one point on the globe to another, or just trying to get from point A to point B, the basic principle that we use in classical physics, for example, is that objects will tend to follow the shortest or straightest possible path that they can to get from one point to another. And so if the space that we're traveling through is curved, then objects will have to follow curved paths rather than straight lines. And if you've ever seen this, there's which I should have put on here, but if you look at the path that airplanes take when they fly across the globe, you draw the map and you can draw a straight line. Well, the shortest distance between 2 points on a sphere is what we call a geodesic, and we actually use the same term in relativity, but it's along a great circle that goes around there. So the path might look curved, but it's really just a reflection of the fact that you're traveling around a curved surface. And so the same thing happens when we travel through any other curved kind of space, no matter how funky it might look. So let's talk about an example of that. Well, in classical physics, when we talk about gravity, which is what we're here to talk about, we think of gravity as a force that causes the apple to fall from the tree. It causes planets to orbit the sun. Right? That's how we think of gravity in this classical pre-relativity physics. But in general relativity, gravity is not a force. There is no force of gravity in general relativity. Objects in general relativity move around these curved paths because they're traveling through curved space. If you think about, you put the penny in the well and it spirals down and down and down. Well, the penny's just moving in what it thinks is a straight line, but it's traveling along a bent surface, and so it goes around and out. That's what happens. That's why, according to general relativity, objects orbit, is because they are thinking they're going in a straight line, and it's the space that's bent. So that's kind of interesting and a little bit funny to think about. Now, I should say that tidal forces, the things that tear you apart when you get close to a black hole in general relativity, those are real. They are a force, but just the simple Newton's universal law of gravitation, that's not a force as far as general relativity is concerned. Okay, so that's cool and weird, but it has another important consequence, which is light. Because in classical physics, light has no mass. And so if you look at the equation for Newton's law of gravitation, it involves mass. And so if the mass is 0, the force is 0. So light in Newtonian gravity feels no gravitational force. But in general relativity, where orbits exist and things fall because space is curved, it doesn't have anything to do with a force. The paths of light rays must curve as well. So I want to do one of Einstein's little thought experiments for you to convince you that this sort of has to be true. And it starts with something called the equivalence principle. And the equivalence principle is one of the fundamental principles on which general relativity is based. And the basic idea of the equivalence principle is that if you're standing there with your eyes closed, whether, often we think of ourselves in an elevator for this. If you're standing there with your eyes closed, you can't tell the difference between you're in a gravitational field that's pulling down, or you're in an elevator that's accelerating upwards. All else being equal, the force or the a downward gravitational field and an upward acceleration will produce exactly the same results if you do an experiment in the elevator. And I don't want to drop the laser pointer, but it means that if I'm standing in an elevator that's accelerating upwards and I drop my wallet, it's still going to fall to the ground at the same rate as if I was standing in a room with a gravitational field and I dropped my wallet, it's going to fall to the ground. So I won't be able to do any experiments that allow me to tell the difference between acceleration and the gravitational field. And there are other more complicated ways to state this equivalence principle, but we won't get into that. So that's the basic idea. Now, then we can do some little thought experiments to play with that idea. So often what we'll do is we'll consider, for example, a light ray that's sent through an elevator. So imagine that I've got a little laser at the placed on the wall, and at some particular instant, I send a laser beam across the elevator. Okay, so it hits the other side and just goes straight across. So that one's easy. Now what happens if instead I have my elevator accelerating upwards? Well, as the elevator accelerates upwards, the light continues its where it's going, and so it hits lower on the far wall of the elevator than it would have if the elevator had just been sitting there. So that's what happens if the elevator is accelerating uniformly. But we've just said that you have to get the same answer if the elevator is sitting in a gravitational field. So if I do this experiment, and I just have my elevator sitting there and I send my laser beam across, well, it's got to give exactly the same answer as the experiment that we just did. So the laser's got to hit lower on the wall than it would have if there had been no gravitational field. So that means that it must be the case that gravity deflects the path of the light ray. So it's an immediate consequence of the equivalence principle that the paths of light rays bend in a gravitational field. Now, there's more to it than this, because if you calculate how much deflection you expect for a light ray traveling through a gravitational field, just based on this equivalence, you get the wrong answer by a factor of 2. And it turns out that it's not just, this is equivalent to thinking about how time is bent by a gravitational field, but space is distorted as well. And so when you have to account for both of those, and then you get the right answer. But so what happens is that when you have light that's traveling past a massive object, the larger the object, the more the light ray is deflected. And for the sun, it's a very small effect for the sun, but it's not so small that it can't be measured. So imagine we're sitting here at the Earth, and there's a star, get above the wall there, there's a star behind the sun. Well, the light that comes from the star grazes the sun and gets deflected so that it would have missed us, but because of this gravitational deflection of light, we actually get to see that star even though it's physically behind the sun. So the star looks like it's over here, but it's actually down here. So there was a very famous experiment done to measure this during a solar eclipse in 1919 by Eddington. And they actually, you can see by comparing the positions of stars before, inside and outside of the eclipse, that this one little star that appeared right next to the sun had actually shifted its position during that eclipse as the light grazed the sun. And so that was a big confirmation of this theory. So strange but true. Now, this is not the only consequence of the deflection of light in a gravitational field. Another way that we talk about this on occasion is what we call gravitational lensing. And so here what we're imagining is that we have a distant source of light, and here we are on Earth, and there's some massive object between us and that distant source. So we'll often call this the lens. And what happens is the light from our source bends around the lens and makes it to us. And why do we call it lensing? Well, the reason is that all of these light rays that were heading off in other directions, they get bent back to us. So light that shouldn't have reached our eyes or our telescopes gets there. And so we get more light than we would have expected to see. The object looks brighter than it would have otherwise. So there's a magnification effect because of the gravity of this intervening mass. Now, there's one particularly cool effect that happens if your light source and your lens and your eyeball all line up perfectly in a perfectly straight line, which is that at that exact moment of alignment, and we'll watch it go by. So here we're misaligned, 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 misaligned. Now we're starting to see weird light bending effects. And now at that perfect instant of alignment, you have light that can come and get bent around your lens, this white object in the center, from every different direction. And so you can actually see a ring, because light can come over your lens and get bent back to your eye, and below and to the sides and at all of the different angles. So that ring is called an Einstein ring. And if you've seen any of the new images from JWST, where there are lots of really beautiful examples of lensing, these, as we have extremely sensitive images of galaxies and galaxy clusters. We're starting to actually see a lot of these, but there are already some very nice examples pre-JWST. But let's imagine then that we have a black hole, which is going to do the most of light bending because it has the strongest gravity. So if we took a supermassive black hole and we put it at the center of a galaxy, and then we looked at it, well, what would you see? You'd see very strong light bending from the light rays that are trying to go around the black hole. You'd see very strong gravitational lensing for stuff that's behind. And you would see, if you're just looking right at it, you would see this sort of Einstein ring. And to put it into a video, so there's our black hole at the center of our galaxy. A very nice animation of this from the National Science Foundation and the Event Horizon Telescope collaboration. So here you're looking at light rays that are traveling and being bent around a black hole. And we're looking in particular at the ones that come to us. What you expect to see if you put a black hole. Are we gonna play that one again? No, okay, let's go back. Let's see that again. So if we look at the light rays that come to our eyeball around a black hole, they're bent in all different directions, but the ones that make it to us get distorted and bent into this ring shape. And so what you're looking at here is sort of the equivalent of an Einstein ring, where you put the lens, your black hole, inside the source. So it gets a little bit more complicated than the basic lensing kind of situation that we think about, but this is what you would see if you could do that observation. And I like to show this figure because this is from 1979. This is a hand-drawn illustration from a paper in 1979 by Jean-Pierre Luminet, doing all the calculations of what would this look like if you actually did this experiment. Obviously, I can't recommend getting this close to a black hole of this size and shining a flashlight on it. It's quite dangerous. But if you were to look at light rays that are traveling near and past a black hole, sort of this size, what you expect to see back, if you could image it, would be this dark region surrounded by a bright ring. And it's worth noting, and it will come back later, that the shadow, we call this the shadow, is larger than the black hole itself. So it's larger than the black hole, but it's still really tiny. So this is a very nice animation from European Southern Observatory. Just to give you a scale, if you were to look at, say, Sagittarius A star, the supermassive black hole in the center of our galaxy, or M87, the size of that shadow, that ring that you're looking for, is about the size of a donut on the moon. And choose your analogy. Sometimes you hear credit card, sometimes you hear a grapefruit. They'll talk about like trying to read the letters on a quarter in LA from New York, or read a newspaper in New York from Paris. It's very, very small. There was a lot of talk about, well, could you ever see a black hole? And aside from the fact that you can never actually see a black hole, the answer that we always gave was, well, you'd need a telescope the size of the Earth to do that. And some people take that as a challenge, right? And so the good folks at the Event Horizon Telescope collaboration thought, well, why don't we make a telescope the size of the Earth? And so what they did was made a network, a bunch of radio dishes, well, technically sub-millimeter, but all over the world, from Arizona and Mexico and Hawaii, and even at the South Pole. Takes a lot of work to get a telescope set up at the South Pole. But this global network of radio telescopes. And what you're doing there is interferometry. So if you link all of the telescopes together in the right way, and that takes precise locations for your telescopes with GPS, and you have to have, you need to know the times of your measurements to extremely high accuracy. But if you can link all of those telescopes together and get them to work as a team, they act like one single dish. Now, you don't have a collecting area equivalent of the Earth, but you do get spatial resolution that is equivalent to that of a telescope with about the diameter of the Earth. So it's sort of like a much bigger example of this. This is the VLA, which, if you've ever seen the movie Contact, shows up quite prominently, a network of radio dishes. And so by networking these stations, radio stations around the world, the HT is able to actually do to resolve scales that are comparable to what is predicted for those shadows. So the two targets that we are most interested in, because they're the only two targets where it's technologically feasible to get images of these shadows, are Sagittarius A star. That's the supermassive black hole at the center of our galaxy, the Milky Way. The mass of Sag A star is pretty well known already. It's 4.1 million solar masses. It's about 26,000 light years to the galactic center. And M87, we now know, is about 6.5 billion solar masses, and it's 53 million light years away. M87 is very, very famous for its jet. So I want to tell you a little bit about these targets and then get to the shadow. So M87, I'll focus on Sag A star, but I just want to show you. This is an image from a big multi-wavelength campaign that went along with Event Horizon Telescope observations of M87. So here's the image of the shadow from M87. But then there's also, we have observations at all sorts of different radio wavelengths. We have observations in X-ray. There were gamma ray observations that have been going on from the ground. So I think this is really lovely to see the sort of progression. The X-ray, this is a Hubble image right here. The scales of these things get bigger and bigger and bigger. You can see this is 0.004 parsecs. And we go all the way up to this image from the Swift X-ray Observatory. Is the scale of that is about 810 parsecs. So we're covering a huge range of scales when we look at this. Now, so studying the jet from M87 is a big draw for Event Horizon Telescope observations and some of the work that I've been doing. But the big headline here is that we have now actually managed to produce images of the shadows of both of these black holes. And there's a really nice image here for a sense of scale to talk about what kind of regions are we talking about. This is the shadow of M87, this dark region, and this bright ring that surrounds it. For scale, this white circle in the center is Pluto's orbit. This is the approximate location of Voyager 1. So this region that we're looking at completely surrounds the entire solar system. The black hole itself, in fact, is comparable to the size of the solar system itself. Now, Sagittarius star is a much smaller black hole. It's about, it's a little bit more than 1,000 times smaller. So the scale of the image for Sagittarius star is a lot smaller. It fits pretty well inside Mercury's orbit. But again, the black hole itself is much larger than the mass of the sun. Sorry, it's much larger than the sun. So we see these shadows, which is what was expected. So our kind of top level headline is that these both Sagittarius star and M87 are consistent with the expectations of general relativity. So I'll give you an example of what that means. What does it mean to say it's consistent with general relativity? Well, general relativity says that this shadow should be more or less circular. It's a little, it takes some work to measure whether something is circular or not in the image, but this is roughly circular, so that's consistent with general relativity. You can, from the size of this circle, you can imagine what's the angle, what angle does that subtend on the sky? And we talk about when we do gravity, we talk about what's called the gravitational radius. And that's sort of the smallest physical scale that we think of in these systems. It's something like the radius of the event horizon of the black hole. And this is 3.77 micro arc seconds. So it's a really tiny little angle. But it's directly proportional to the mass of the black hole. And so from the size of this thing, we're able to measure the mass of the black hole. And there was actual uncertainty about the mass of the black hole in M87. So it's very nice to have this resolved. So that's a 6.5 billion solar mass black hole. Now, Sagittarius star broadly looks similar, but it's a little bit different. There's still this dark region in the center that's a little bit harder to quantify, but it's still roughly circular. That size of that region is consistent with the 4.1 million solar mass black hole that we know is there. And there's also these three bright spots, and it's really not clear what these represent. Sagittarius star is much smaller than M87, and one of the things that means for black holes is that it takes a lot of time for stuff to orbit. So if you think of M87, it's much larger. Things orbit it takes a lot longer. So when you're doing your observations, the black hole sort of lumbers around. But Sagittarius star is kind of whizzing all over the place. It's harder to keep track of where stuff is. And in fact, it's much more difficult to construct an image like this for Sagittarius star, which is why it took 3 extra years. These data that I'm showing you were collected at the same time, but it took an additional 3 years to figure out how to produce these images. It's much more work went in by this very large team. Yeah, question.
What is the effect of a magnet or the magnetosphere of the
So one of the
Can you repeat?
yeah, so the question is, what's the effect of the magnetosphere, the magnetic fields in the plasma? So one of the things that we can do with these data, and we just last year published these results for M87. What the magnetic field does, and what the electric and magnetic fields in this plasma do, is they polarize the light that you can see. So if you can map how the light that we're seeing from this gas, right? This is a view of gas that's falling onto the black hole, and it's lensed and distorted into this ring shape. If you can measure the way that that light is polarized, then you can learn something about the magnetic fields. And so last year for M87, we published maps of the polarization of this image and inferred something about the magnetic field. So you can measure that, and it has a definite effect on the measurements. It doesn't directly, as far as I can think of off the top of my head, change the intensity of the image very much. But
universe is a plasma, and plasma is affected by magnet.
sure, but the plasma itself is generating the magnetic field. So we're not thinking of the black hole itself as like a magnet, right? The magnetic field that we're interested in is carried by the plasma rather than affecting the plasma. So here we go. So Sagittarius star is extremely variable. It's also right in the middle of the galaxy. And if you ever tried to do, say, any optical observations of the inner galaxy, you know, there's dust. And if you, the Event Horizon Telescope operates at 1.3 millimeters or 230 gigahertz. And the effect of interstellar dust and electrons is a lot less significant at those frequencies than it is in the optical, but it still can interfere. There's scattering that can happen that can still interfere with your data points a little bit. So there's variability, and there's scattering, and there's some other effects that mean we're not entirely sure whether these blobs are really there or whether they're just an artifact of trying to do this imaging that's much harder for this particular object. So so we have to be kind of honest about that. They show up in our reconstruction of the image, but we're not exactly sure if they're real.
Good question.
Yeah.
You said these are the gases that we're seeing.
Uh-huh.
Do they rotate around the black hole in a plane, or is it just a sphere of gas that's rotating around?
For these sources, it's probably something like a spherical flow of gas onto the black hole. So if you looked from a different direction, you would still see that ring, but you would be you're looking at if I go back to that image, the point where you're sort of seeing lensed is the point that's behind the black hole. So if you look from a different angle, you would see different gas magnified, but you would still see more or less the same thing.
Wouldn't you also see the gas that was on the near side?
It's if you track really carefully the light that that goes around the black hole and makes it to your eye in that particular direction, the stuff that you see brightest is the stuff that's right there. That is directly behind the black hole. Then fainter than that, you see the stuff that travels halfway around the black hole and comes to you. Fainter than that still is stuff that makes a full loop around the black hole and then gets to you. So all of those pieces are in there, but the stuff that's brightest is the stuff that's behind it. There's actually been a lot of work on that recently. So this is still something that we're, can we constrain those things better and better? So one of the things that we found, and this turned out to be kind of a funny coincidence, you can think about black holes rotating. So they have a spin axis just like the Earth. Well, it turns out that we're looking at the poles of both. We're looking sort of what we would call face on to both of these black holes. in completely different environments, looking sort of into the center of the galaxy, you wouldn't have expected that you would be looking at the bottom or the top of Sagittarius star. But that is the way it seems, that we're looking pretty close to the rotation axis of both of these black holes. So that was kind of a funny surprise. And it was a funny surprise that it was true for both of these black holes that we have been able to image. Now, unfortunately, there are not other black holes that are large enough, right? Even the Event Horizon Telescope is limited in its resolution. There are not other black holes that are large enough to see the shadow. There are black holes, plenty of other systems that we're looking at that are nice targets. We can study their jets and their interactions with their environments, but everything else is too small to actually see that ring. Question.
So that means that our black hole is tilted 90 degrees relative to the.
Yeah,
galactic
probably.
axis?
So the question is, does that mean that the black hole is tilted 90 degrees relative to the plane of the galaxy? And it may not be exactly 90 degrees, but yeah, it appears to be tilted in the same way that Uranus is tilted relative to the solar system plane. Now it's very hard to tilt a black hole, right? To push on a black hole and make it spin faster or change the direction that it's rotating takes a lot of oomph. So we'll leave that for a puzzle for right now.
Is the black hole spinning, or is it the mass around it?
The black hole is spinning, and you can also ask, is the stuff that's swirling around it, you can ask whether it's swirling in the same direction as the black hole or in the opposite direction. And we can also constrain that as well. So the stuff seems to be spinning in the same direction as the black hole. We call that a prograde orbit versus retrograde. Yeah, so we have constraints on both of those, and we haven't been able to yet really measure how fast the black holes are spinning, but it seems to be that they are spinning and not that slow. Question.
The picture look like if the axis has a different direction.
Yeah, so at some of the question is, what would the picture look like if you were looking from a different direction? And it's a generic feature. You see this especially in MA7, it's easiest to see that one side of the image is brighter and the other side is fainter. Part of that is because some of the stuff is coming towards you and some of the stuff is going away from you. So the part that's moving, the gas that's moving towards you is brighter because of relativity. That is sort of consistent with what we think of as a crescent. So and I'll show some images in just a minute. Generally, you expect bright crescent features more or less no matter what direction you're looking at. So you expect to see a ring, and you expect to see one side of it will be brighter than the other. And that's a pretty generic feature, and the size of it is pretty much independent of the direction that you're looking. You might see some other features depending on exactly what direction you're looking at, and is there a jet or is there not a jet? Those things can have effects, and we're still working on getting as much information out of these systems as we can. Okay, so I want to give you a little bit more context for Sagittarius star. So Sagittarius star was discovered as a radio source in the center of the galaxy in 1974. And what's really interesting to me, the thing that sort of makes it click for me, is that it took decades to find it at any other wavelength. Right, so that already tells you something about it's relatively much brighter in the radio than it is at other wavelengths. So part of the reason for that is that the galactic center is really crowded, and so it's hard to distinguish the thing that's at the very center from all of the other stuff that's buzzing around it. But eventually, this happened, and so Andrea Ghez at UCLA won the Nobel Prize for this work. What I'm going to show you is a time lapse of infrared images of the galactic center, and what you're going to see here is these stars represent stars in a cluster at the center of the galaxy, and if you watch them for 20 years, Now, so these images started in 1995, once it was finally technologically possible to resolve this star cluster. What you see is the stars buzzing around. So if you focus on this particular star, which is called S2, you see it makes a little loop. So you can actually see the stars orbiting something. And if you look carefully, they're not orbiting something that you can see. So these early constraints on the motion of stars early in the center of the galaxy tell you that at least that inside a region in the center, at the center of the galaxy, a region that's not bigger than 1/6 of Mercury's orbit, there's at least 100,000 times the mass of the sun. And it's not something that you can see. So, eventually, if you calculate the density that's inferred of this point, it's something like 1 trillion solar masses per cubic parsec or something. It's a huge density for what you infer for this thing that isn't there. And so the only thing that we know of that could be is a black hole. But then the fact that you can't see it is strange. Where is it? Well, if bright quasars that we look out in the distant universe, that we can see them from billions of years after their light was emitted, if you make the analogy that those are like a speeding train, Sagittarius star is sort of the equivalent of a hummingbird. So why is it that our black hole is so faint? What is it? We don't, astronomers, we don't like to live in, we don't like to occupy special places. We want everything to be more or less the same everywhere. So it's very strange that we live in a galaxy where this black hole is so very, very quiet. But there's a flip side to that puzzle, which is that, it's Sagittarius star is a lot smaller than M87. It's a lot more variable. And so even though it's very, very, very faint, when we look at it, we see that it flares every now and then. And so this is a sort of imaging equivalent. These are Chandra observations where there's Sagittarius star right here, and it goes boom, and then goes away. So it shows these flares, and they happen on average about once a day. As far as we can tell, it's totally random. They last about an hour, sometimes a couple hours, sometimes only 10 minutes or so. But these little pops, and we don't know what they are. This has been another long-standing puzzle. What's going on with these flares? So this has been one of the things that I've been interested in for a long time. So here's just an example of sort of a compendium of some flares. This is about a month of data taken by the Chandra X-ray Observatory, and I've taken out all of the gaps between the observations, but you can see flare, 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 flare. And then kind of nothing, nothing, nothing flare. And here's a zoom in on some of the different flare light curves. So this is just brightness on the y-axis and time on the x-axis. And sometimes, this is about 6 hours. Sometimes we see a bunch of flares all together. Other times we'll see nothing over the course of several days. This is a flare that was observed by the XMM Newton Observatory during actually this spring's Event Horizon Telescope campaign. So we're really trying to keep studying these flares, and also in conjunction with the EHD. So where do they come from? Well, they don't last very long. It's only an hour. It's pretty short. So it's hard to make big things act quickly. So probably these are regions that are small and close to the black hole. And one of the kind of most prominent explanations is that you're looking at turbulent plasma near the event horizon, and so you see this what we call reconnection events. It's a little explosive plasma event. So this is a simulation. Finally, the simulation technology is getting good enough to be able to reproduce these kind of events in the
High temperature, plasma,
incredibly high.
like X-ray.
So in fact, when you talk about the temperatures of the electrons in this plasma, it's 1 trillion degrees. And that's what you would infer if the emission that you were seeing was thermal. These are probably not thermal electrons. So this gas, it's very, very, very low density. So you don't get a lot of collisions. So it doesn't glow in exactly the same way that the surface of the sun does. And so it's much fainter in the X-rays that you would otherwise expect. But yes, very, very energetic particles. And so what you would hope, there was a recent paper from 2018. This is gravity. They're doing infrared interferometry. And they measured a flare in the infrared. And they looked, this is the position of their little source during this flare. And they found that it seems like it moves in a circle. So they think they're seeing that this flare is actually something that might be orbiting the black hole. And so one of the hopes is that we've been studying the flares in the X-ray for so long. We're doing these observations with the Event Horizon Telescope. It would be really nice to see them together. So why are the X-rays? Well, it actually goes to this question. So we're seeing these explosive plasma events. That's what we think these flares are. We're talking about, that means there are energetic particles involved. And when there are really energetic particles around, you get X-rays. And so what it means is that X-ray observations are really sensitive to the plasma physics, the particle physics that's happening right near the event horizon. So that's why it's really nice to have these observations that go together. And we were really close. We were so close. These are 3 days of observations from the 2017 observing campaign. And so here's in blue is the Chandra light curve. So we have brightness on the y-axis and time. This is April 6th. This is April 7th. Nothing happening on either of these days. In green is the data from the Event Horizon Telescope. And then on April 11th, there's a flare. And just after the flare, the Event Horizon Telescope starts observing, and they actually see really strong variability. So we were like minutes away from catching this. This is a thing that we've been trying to do for years now. And so for me, this is really exciting. This is a great reason to keep trying to do what we're doing. Again, these are random events, so you can't predict when they're going to happen. So you just got to keep looking and keep your fingers crossed. But this variability here that was seen just after the flare in the Chandra data, where it goes boom, and then there's strong variability that's observed by the Event Horizon Telescope. There was just a paper out really a few weeks ago, I think, showing that the data from ALMA in Chile, that those data were consistent with a hotspot that was orbiting the black hole at that moment. Now, it doesn't have the full imaging of the Event Horizon Telescope, so there's not actually an image of this. This is just an animation, but you have at that time, the implication is that you have a blob that's orbiting the black hole about once an hour, and therefore traveling at about 30% of the speed of light. So we were very, very close to being able to have an image of that. And so I think that's so exciting. So part of that's sort of the context for these multi-wavelength observations of Sagittarius star and M87. So how do we actually use those multi-wavelength data to help us learn about these black holes? Well, theoretically, you can produce images, you can make simulated images. What would the Event Horizon Telescope see if the black hole was spinning in this direction, or spinning in that direction, or tilted, or a spherical accretion flow, or a flow with a jet? Or you can imagine all sorts of different scenarios, different assumptions that you might make about how the plasma works. And predict, you get a whole library of all these possible images that you might see. So we have this big catalog in the collaboration of possible images. And then the idea is to compare those images to the actual data and use them to interpret, well, which of those physical scenarios is consistent with the data. And it turns out that a lot of the time, lots of different models, we would call them, can explain the data, that the images, the rings that are observed by the Event Horizon Telescope. And so at that time, you need to turn to other methods. You need other information to decide which of those models is better. And because X-ray observations are so sensitive to the details of the plasma, they can help you decide which, in other ways, which of those models work. So if something predicts really bright X-ray emission, but that's not what we observe, we can rule that one out. So, so it's a kind of complementary information that helps us pick between this very big library of images that we might expect to see. So just to give you a little sense of what those measurements might look like, these are X-ray spectra of Sagittarius A star. So again, I have a measure of brightness on the y-axis and energy on the x-axis. And the flare spectrum I have in black and green from two different telescopes from Chandra and the New Star X-ray Observatory. So the flare is up here, it's brighter. And when it's not flaring, it's fainter. And that's this orange data set. So what we can do is during these flares and outside the flares, we can measure how bright the system is in X-rays. That's a useful constraint, like I said, for testing those different models. We can also, if we get fancy, we can measure the shape of the spectrum. So these are the kind of measurements that we can do that help to interpret those data. And this is work that has been done with a handful of different students at Villanova, undergraduates, Jaden Ancharsky and Caleb Kwan. So this is the kind of information that my group and I have been providing to the HT as part of this multi-wavelength campaign. And there's a lot more to come. There's we keep doing these campaigns. The Event Horizon Telescope observations primarily happen in the spring because that's when the weather is best at telescopes like ALMA and the way that we can work out the schedule for those observations. So we're gonna keep doing these observations to try to, for Sagittarius star, catch flares. For M87, we're gonna keep trying to study that jet. And again, because we have such big and beautiful data sets already, there's already a lot we can do. This is a close-up of that X-ray jet as seen by Chandra in M87. And my postdoc, Ramesh Thamapa, is working really hard on trying to understand the structure of this jet and how it changes over time. So hopefully we'll have some nice results about that. I don't want to scoop him on his own work, but there's neat things to come, I hope, in the very near future. So let me wrap up and leave some more time for questions. I hope I was able to convince you at the beginning that gravity warps the fabric of space, and that leads to the deflection of light in gravitational fields. And as a consequence of that, we have exciting phenomena like gravitational lensing that really makes it possible for produces these shadows that we are very happy to try to observe with the Event Horizon Telescope. And by doing observations, if you're gonna look at a black hole with a telescope the size of the Earth, well, you might as well look with other telescopes at the same time. And so those observations at other wavelengths really provide important physical context and a lot more information that we can use and to help interpret those observations and get a better understanding of how these black holes work to begin with. So I'll stop there and take any other questions.
What happens when dark matter? What happens when dark matter interacts with the black hole?
So the question is what happens when dark matter interacts with the black hole? And as far as we know, when you interact with a black hole, either you get away or you don't, right? So what's important for as far as the black hole is concerned is what's the mass and what's the energy. So if the stuff falls into the event horizon, it just becomes part of the mass of the black hole. And if it, if you have a slingshot orbit or you manage to fly by or escape, then it just flies by and escapes. But as far as we understand dark matter, which is not very much, it behaves the same laws of gravity as anybody else. So if it falls into a black hole, it becomes part of the black hole and it gets crunched in the middle. And if it doesn't, then it just flew by. So I would say it's just like any other matter in that context. Yeah.
So thank you for the talk, really, really great. Hi. So you talked a little bit about the size of the singularity, or more correctly, you didn't talk about it. And so, very often we don't talk about absolutes, we talk about comparables. So would Sag A and M87 have the same size singularity, and we just don't know what it is? Or, we know the event horizons are different. but-
Right. The
Right.
singularity, to the extent that singularities exist, which is maybe not, the singularity would be the same size. It has a radius of 0.
Okay.
So 0 is the same no matter how many factors of 1,000 you multiply it by. Now, the question is then what happens, at those sizes, you need to start thinking about quantum mechanics, right? Because you see these gravity wells and the rubber sheet analogies for that describe space and time in general relativity. Those are smooth, and quantum mechanics doesn't really do smooth. Quantum mechanics does fluctuations and uncertainty. And so if you want to think about, well, what is a singularity like, you need a theory of quantum gravity. And so in principle, you shouldn't be able to have anything that is smaller than what we call the Planck length. And so a black hole that would have a radius of the Planck length is about a microgram. It weighs about as much as a grain of sand. So the Planck length is really small, but it's still finite. So the thing about the singularity is that from the outside, once you make the object smaller than the event horizon, once you push the sun smaller than 3 kilometers, whether it forms a singularity in the center or not, whether it collapses all the way to 0 or just most of the way to 0, the event horizon is still there, and it's still a black hole as far as the outside world is concerned. So truth is, I don't know the answer to that question, but I think that we don't really understand singularities that well at all.
Thank you. You mentioned that spatial resolution with the interferometer, we're hitting the limit. You said we had 2 candidates and looked like 2 were examined.
Yes.
Not to be punny, what's on the horizon?
So I had a student who was working with me on other topics, but she had a summer internship at MIT, where she was looking at this is Catherine Petretti. She was looking at what would you get if you put an EHT station in space? Because then you have what limits your ability, if you think about the diffraction limit, which is how blurry your images are going to be, it depends on the diameter of your telescope. So if you make your telescope as big as the Earth, that's about as big as you can go on the Earth. But if you can put a station in space, then you have a much wider baseline. And I don't have any animations of it, but one of the things that you're counting on when you do this interferometry, this particular kind of interferometry is called aperture synthesis interferometry. And as the Earth rotates, the example of the sort of analogy that they gave during the EHT press conferences is like breaking up your mirror into a bunch of little pieces and sprinkling it all over the surface of the Earth. Well, as the Earth rotates, you get more and more view of your target. So you visualize what's happening on different baselines between different telescopes. And so if you put something in orbit, then it's moving and you get to see a whole lot more view. So you can actually really improve your resolution and sensitivity a lot. So there is a possibility of obviously that needs funding, but there's that possibility. So that's one thing. What's that?
I found Lou to write a check or treasurer.
That would be lovely, yeah. So that's one thing. Now, also the diffraction limit depends on the frequency that you're observing at. And so the collaboration is working on going to slightly higher frequencies, which will improve the sensitivity and the resolution a little bit. Eventually, you run into a problem with interstellar scattering. And so there's a kind of a sweet spot there that that allows you to get good images and not be too subject to problems in the interstellar medium. So that's it then, but there are also lots of other targets, like I said, where papers have come out, and obviously they're not the shadow images, so they haven't gotten quite as much press, but there's lots of good jet physics and relativity testing to be done. Yeah.
Great talk.
Thank you.
Love the images when they came out and in your talk. What is the next most likely candidate to be imaged as far as supermassive black hole?
Yeah, so there's a chart, and I looked for it and I couldn't find it. There was a chart of the angular size of black holes by mass and distance, or I don't remember what the other axis was. I couldn't find it. I was trying to pull it up so you could see it. But really, these are the only two black holes that are large enough. Our galaxy, the Milky Way, has probably millions of black holes in it. Most of those are remnants of individual stars that have exploded and left a black hole behind. Those, the scale of these images is tens of micro arc seconds. The size of those black holes, the stellar mass black holes, would be nano arc seconds. And all of the other black holes in nearby galaxies are the combination of too small and too far away to actually be able to see the ring. So there are, as I said, there are many other targets that the Event Horizon Telescope is observing to study their jets and to study their accretion processes. We can learn a lot about those systems without having the actual image of the ring. But there are no other targets that in the foreseeable future we're going to be able to get these rings for. So we're working on improving our understanding of these two sources, and then also getting lots of other information about other targets, jet physics and things like that.
Hi, can I ask a few questions from YouTube?
Please.
That isn't working very well. So Roy Patton asks, how much larger is the shadow compared to the actual black hole?
It depends a little bit. The question is how much bigger is the shadow than the black hole itself? It depends a little bit on the spin of the black hole, but it's about 5 times larger than the radius of the event horizon. So if this is the radius of the shadow for M87, the black hole itself is something like 5 times smaller. So the whole thing is about, the whole diameter of the shadow is about 10 times the radius of the black hole.
Got it. So actually, that was the only question. There was a lot of text and sorry.
That question in the back?
Yeah, that wasn't working.
Falling into the event horizon, come to the event horizon.
You've come to the event horizon. So you're telling me 5 times the size. It sounds like, okay, I'm falling in, I'm going to splat onto the black hole. What is it more? I'm falling into the event horizon. I'm falling into the singularity.
So the event horizon is kind of the part that represents the hole, right? This is a thing that you could fall into in the same way that you could fall into a hole, except that if you fall into a hole on Earth, you can climb back out again. So the event horizon is it's the finish line for your race. Once you've crossed that, you can't get back out. But it's not a solid thing. It's an imaginary surface. So as you fall towards the black hole, bad things start to happen, right? Because the closer you get to the singularity, the the stronger, if you're falling sort of feet first, the gravity on your feet starts to become stronger than the gravity on your head, and that tends to stretch you out. It pulls harder on your feet than on your head, and eventually those forces become strong enough to tear you into your constituent atoms and molecules. So we call that spaghettification because you get stretched into a long, thin paste. And so for a small black hole, that happens before you reach the event horizon. It happens outside the black hole. For a really large black hole like M87, you actually wouldn't really feel much of anything. If you kept your eyes closed, you could cross through the event horizon without experiencing any particular ill effect. But then you're trapped in there, and it's only from there, it's only about an hour of time to fall inwards. The weird thing is that once you go inside the event horizon, it's not possible even to remain at one position. One way people like to talk about it is that space at that point is falling towards the center faster than the speed of light. And so it's like a river going downstream. You can't even hold your position, much less head outwards. The center of the black hole becomes your future, is a weird and upsetting way to think about it. But yeah, so as you fall in, you're approaching this thing, and once you cross this dotted line, then you're stuck in there, and no matter what you do, you're going to end up at the singularity. Does that kind of answer your question?
Yeah, the edge of the black hole inside the event horizon. Doesn't seem to be an edge. Black hole doesn't seem to have an edge.
Right, the event horizon is the edge.
I thought the case was that at the event horizon, the tidal forces are infinite.
The tidal forces are infinite at the singularity.
Right, so by the time, long before any object that is made up of molecules gets close to the event horizon, it's going to be broken up into its constituent atoms. And then the interesting is, then will the atoms then be broken up into subatomic particles? And then you get back to the question of what happens with, the quantum particles in that kind of gravitational field. And I thought I heard you say earlier, we don't have a physics that describes that terribly well.
That's right. Well, we can describe the motion of individual particles in a gravitational field very well, but it's the question of what does space-time look like on scales that are that small. That gets tricky. But it's true, in fact, that the tidal forces at the event horizon are finite. Finite, and in some cases they are small enough as to be negligible. What's important for the tidal forces is how close you are to the singularity, and that depends on the mass of the black hole. So at the event horizon, for a bigger black hole, the event horizon is physically even farther away from the singularity. And so the tidal forces are actually weaker for big black holes and stronger for small black holes. So that's a weird kind of counterintuitive thing about it.
Yeah, so more questions from the net. If bright spots indicate portions that are traveling towards us and dimmer side is traveling away, how does that agree with the idea that we're viewed from the pole of the black hole?
Yeah, so we're not exactly, it's not exactly face on. So I think the angle in M87 was something like 17 degrees. So there is a little bit of a tilt, and this stuff is moving really fast. You're talking about stuff that's orbiting the black hole at a significant fraction of the speed of light. So even a little bit of tilt, you get that kind of boosting effect.
Cool. Just one more thing. So looking at the slide you have up now, M87's black hole is about the size of our solar system. Is that correct?
Yes, that's right. So the black hole itself is the size of the solar system, and the shadow is larger. There's a question here in the room as well.
Yeah, how close to the speed of light then is going to, from the event horizon to the singularity? How fast are the?
Could you repeat the question?
how fast are the particles moving from the event horizon to the singularity?
So once stuff falls in, so there's this weird, this is where things get relative. You think about dropping something into a black hole. One of the weird things that happens with relativity, and you can do the elevator thought experiments to convince yourself of this, is that time runs slower in a gravitational field relative to far away as well. So you have, and you also have a gravitational redshift where light that's climbing out of a gravitational field looks redder than it would. So if you drop a light bulb towards a black hole, the light that you see from the light bulb, it starts to move slower and slower and slower. And that is, the light bulb appears to be falling slower and slower and slower. And it gets fainter and fainter and redder and redder and redder. And in fact, from the outside, you never see that light bulb. Not only do you never see it get into the black hole, you never see it reach the event horizon. At t equals infinity, then it reaches that event horizon. Now, the actual amount of time that it takes for the light bulb to fall in, if you're standing on a light bulb watching your clock, it might be a fraction of a millisecond. So from the time that it takes to fall from the event horizon all the way to the singularity can be very, very, very short. So imagine crossing the entire solar system in about an hour, which is about how long it would take to fall from the event horizon to the center of M87. You're talking about, I have to think about my Pluto orbital radius divided by hours to get the speed of light, but it's a significant fraction of the speed of light. So it's not light speed, but it's close to it. Yeah.
He described that as only an hour, but it sounds like a very long hour.
Well,
Screaming the whole way down.
wouldn't be able to scream for that whole time.
Well, you would be baked to a cinder before you broach the.
The radiation environment is a detrimental as well. Yeah.
So I understand that the ring of light that we're seeing is gravitationally lensed light from an object behind the black hole. How much of that emission is from the plasma immediately surrounding the black hole? Or do we not see that because it's inside the shadow?
So that what you're seeing is the plasma around the black hole, but you're seeing the stuff that's right behind it. So it's, the black hole is surrounded by plasma, and you're getting a lensed view of the stuff that's right here.
Right, so do we see any emission from the plasma itself?
That is the emission from the plasma itself. Oh, well. So I would say that this is the emission from the plasma itself. It's just lensed. There's a weird distinction in there, but I'm not sure that we're on the same page about the question, right? So the emission that you see from the plasma itself, there's the stuff in front of it that doesn't actually contribute as much because the stuff that's behind the black hole is getting magnified. So it's easier to see that magnified light. So this is the light. You've seen Interstellar?
Yeah.
That distorted view of the accretion disk around the black hole, right? This is sort of the equivalent of what you're seeing there. So this is the light from the plasma around the black hole. It's highly distorted because of the black hole's gravitational field.
So it's light from the plasma on the backside of the black hole.
Yes,
Okay.
and you don't get much from relatively you don't get much from the stuff in front because of the magnification due to the gravity. Does that make sense?
I think so.
May I reformulate a little bit this conversation? As far as I understand you, we see bright light from plasma behind the black hole, but we don't see bright light from side plasma because it's just lasers in the other direction, not towards us.
That's right. Somebody else looking in a different direction would see that light lensed. So if somebody was 53 million light years on the other side of M87, they would see the light from the plasma that's between us and the black hole.
It would be fair to say, I think, that the black hole emits in all directions relatively the same amount of energy. So the energy that's being lensed to us happens to be that energy that comes to us. But it is, do you have any sense of, if there was 10 units of energy that came off the thing in mass, how much would come out the lens thing?
Right.
1/100 of 1%, 1,000th of 1%, how much?
Yeah, so yeah, as far as we are modeling these systems, they appear to be sort of spherical. Now the jets kind of break that a little bit. But they're at the scale that we're looking at these images right now, the jets are hard to see. So we're hoping to get better constraints on jets with future observations. But yeah, so you're looking at this thing that's fairly spherical. So is the question sort of how much is that light magnified? Like what?
No, how much quantity of energy, so you're saying that what you're seeing is some stuff behind the black hole from your perspective pushing forward, but the black hole essentially is a spherical radiating object. So you're seeing a very, very small percentage of the energy. I'm thinking. Any sense of how much that is?
Well, the stuff around the black hole is radiating.
I meant that generic.
So even M87, which is still substantially brighter than Sag A star in terms of its total, the emission that comes, we talk about we sometimes, if I say informally the emission from M87, what I mean is the emission from the stuff around M87 or Sag A star. M87 is quite a bit brighter than Sag A star, but it's still quite faint compared to quasars. So our reference point for bright objects is the Eddington limit, and the Eddington limit is the luminosity at which light pushes on stuff. Light can exert pressure on gas, and so if you imagine throwing a bunch of stuff onto a black hole, well, that stuff gets hot and it glows and emits light as all of these things do. Eventually, it can get so bright that it pushes the stuff away.
Yeah.
So the point at which the brightness prevents future gas from falling inwards, that's the Eddington limit. And it's a good benchmark for really bright, right? In order to stop all of this stuff from falling onto a black hole, it has to be quite bright. Sag A star is something like 10 to the minus 10 in Eddington units. And M87 is 10 to the minus 6. I don't remember the exact number off the top of my head. So it's still really faint. There's still, if you look and you assume that this is coming off in more or less equally in all directions, it's still not very much energy as far as what could be available if a bunch of stuff was
as
falling.
Opposed to a quasar doing a jet that's literally pointing it.
Well, yeah, and even if you ignore that part, you're getting a lot more energy out of other systems, and that's just because more stuff's falling in. The more stuff falls in, the more light you get out, and so these systems are still pretty quiet. It actually makes it a lot easier to zoom into the black hole itself. If there was more going on, it would be a lot harder.
Got it.
We'll do another 1 or 2 quick questions.
As it's falling into the event rise, are you going directly in or are you staying in like a whirlpool?
It's up to you. It's a choose your own adventure. So so you can have all sorts of different kinds of orbits. You can fall directly in, you can have circular orbits. The funny thing, this ring, so mostly what we're seeing here is the gas. But if I go way back to my old image from that 1979 paper by Luminet, what do you expect to see? No, there we go. This bright ring, this bright ring is very narrow. It's called the Photon Ring, and it's actually where light can orbit the black hole. So there's this very particular radius where light rays themselves can orbit the black hole, and they're not stable, but that represents the boundary of the shadow that you expect to see. So then you can have orbits that spiral inwards. You can have orbits that are like regular orbits, but they precess a lot. You can have circular orbits. There's all sorts of different kinds of orbits that are allowed. And my students in general relativity next semester are going to get to study all of those in great detail.
But what about the energy output? Is it uniform coming out or is it directional? Some areas more than others.
Yeah, that really depends on what's falling in. If the stuff is falling in more or less equally in every direction, then you would expect to see that the light comes out more or less in every direction. But if you have a lot of stuff, that would tend to coalesce into a disk that we would call an accretion disk that's really spiraling sort of cleanly in one plane, then depending on how much stuff is falling in, you can get very what we would call anisotropic emission that's very different in different directions. So that makes it harder. So it's nicer to look at these systems where there's not a lot of stuff falling in because it's diffuse. And so it looks more or less the same in every direction. But there are other systems where it doesn't work out that way, and that's trickier.
So the black holes, there can be different kinds of black holes, not all at the same time.
Sure, yeah. Well, we see black holes doing a whole range of different things. We don't see a lot of black holes. Like we know of dozens of stellar mass black holes in our galaxy, and we study those a lot. They're called X-ray binaries. It's sort of the other half of my hat that I wear, and they tend to get very, very bright. They don't really do much of anything like Sag star. So yeah, we see a whole range of behaviors. Some of the stellar mass black holes in our galaxy behave a lot more like the distant quasars that are really bright and really active. So yeah, there's a whole big fun range.
All right, any other questions? Anything on YouTube?
No, YouTube, I lost power. We had 25 people when they asked 5 or 6 questions, so.
All right.
Pretty
Thanks,
good.
YouTube.
All right, let's
Yay,
thank
YouTube.
Joey for a great talk. Thanks, everyone. Want to adjourn it or, well, we don't need this.
Okay, all right. Thank you so much. Thank you, Dr. Nielsen, for a great talk. Thanks for everybody for coming. And hope you enjoyed it. And we'd like to see you here next week next month, or coming to any of our activities. Those of you who are from the Physics Teachers Association, and have a great time tomorrow at your real meeting, right? Yeah, be good. Thank you so much.
This was just the teaser.
And hang on to your name badges for tomorrow. Thank you, sir. Great job.
Thank you so much.
Thanks very much. Night to you too.
I had spent a career, 46 years working. And I taught at the medical school.